White hole theory. In the grand, silent theater of the cosmos, there is no monster more famous, more terrifying than the black hole. It is the ultimate cosmic trapdoor, a point of no return where gravity becomes an absolute tyrant. We know the rules. Anything that crosses its event horizon, be it a stray asteroid, a giant star, or even light itself, is lost forever, crushed into an infinitely dense point called a singularity. But what if the universe plays a deeper, more symmetrical game? What if, for every cosmic drain, there is a cosmic fountain? For every ultimate taker, there is an ultimate giver. This isn't just poetry, it's a mind-bending possibility that lurks within the very same equations that gave us black holes in the first place. This is the story of the black hole's secret twin, its perfect opposite, the white hole. A white hole is, in the simplest terms, a black hole playing in reverse. Imagine recording a video of a black hole devouring a star and then playing that footage backwards. Instead of a star being pulled apart and swallowed, you would see a chaotic burst of gas and light erupting from a central point, coalescing back into a star that then flies away. That eruption, that one-way exit from oblivion, is the essence of a white hole. It is a theoretical region of spacetime that nothing can enter from the outside. While a black hole's event horizon is a one-way membrane to get, a white hole's event horizon is a one-way membrane to get. Matter and energy can, and in fact, pour out of it, but nothing is ever allowed back in. It's a source, a cosmic spring that only ever gives. So, where did this bizarre idea come from? It wasn't just a science fiction writer's dream. The concept of a white hole emerged directly from the mathematics of Einstein's theory of general relativity. In 1916, just after Einstein published his revolutionary theory, a German physicist named Karl Schwarzschild was the first to find an exact solution to Einstein's complex field equations, describing the gravitational field outside a single, non-rotating, spherical mass. This became known as the Schwarzschild solution, and it perfectly described what we now call a black hole, complete with its event horizon and central singularity. For decades, that's where the story ended. But physicists realized that Schwarzschild's solution was incomplete. It only described a part of the spacetime it predicted. When mathematicians and physicists like Martin Kruskal and George Sekaris decided to explore the mathematical landscape of the solution, a process called creating a maximally extended spacetime, they found something shocking. The equations didn't just describe a region you could fall into. They also described a region you could only come out of. The mathematics naturally included a white hole, eternally connected to the black hole in a sort of mathematical Mobius strip of spacetime. According to this pure, idealized solution, the black hole and white hole are two ends of the same tunnel, a structure known as an Einstein-Rosen bridge, or what we more popularly call a wormhole. This is where the dream of white holes runs into the harsh wall of reality. The Schwarzschild solution describes an eternal black hole, one that has existed for all of time and will exist forever. This is a purely mathematical object. Real black holes in our universe aren't eternal. They form from the collapse of massive stars. This physical process of formation doesn't seem to produce the necessary geometry to also create a white hole. It's like having a blueprint for a house that includes a magical self-refilling pantry, but the actual construction process only allows for building a normal pantry. The math allows for it, but the physics of reality doesn't seem to lead to it. Furthermore, white holes are predicted to be spectacularly unstable. The very definition of a white hole, a place that violently rejects anything trying to get in, is its own undoing. Think about it. If even a single photon of light, a single particle of dust, were to travel towards a white hole, it wouldn't be able to cross the event horizon. But where would it go? That incoming particle, however small, would have its energy build up infinitely at the boundary, and its gravity would become immense. That tiny disturbance would be enough to trigger a catastrophic collapse, instantly turning the white hole into a much more stable, familiar object, a black hole. In a universe filled with stray photons, cosmic background radiation, and interstellar dust, a white hole would be snuffed out the instant it was born. So, we have this beautiful, elegant mathematical object that is the perfect mirror to a black hole. It's predicted by the same theory, a testament to the symmetrical power of Einstein's equations. Yet it seems to be forbidden by the messiness of the real universe. We have never seen evidence of one. No telescope has ever detected an inexplicable fountain of matter spontaneously erupting in the void. For most of the 20th century, white holes were dismissed as a mathematical curiosity, a ghost in the machine of general relativity, a solution that was technically correct but physically irrelevant. They were a fascinating footnote in the cosmic story. But what if that footnote was actually the headline? What if their purpose wasn't to exist, but to have existed once for one brief, universe-defining moment?
Universe creation theory. If white holes are so unstable that they can't exist in our current universe, then what's the point? Why do some of the most brilliant minds in physics keep returning to this ghost in Einstein's equations? The answer is perhaps the most audacious, mind-bending idea in all of cosmology. What if the Big Bang, the very origin of our 13.8 billion-year-old universe, was a white hole? This isn't just a wild guess. It's a speculative but compelling idea that attempts to solve some of the deepest puzzles about our own creation. The standard Big Bang theory tells us that the universe began as an infinitely hot, infinitely dense point, a singularity which then violently expanded. But the theory never explains the singularity was or what came it. It's simply the starting line where our understanding of physics breaks down. This is where the white hole enters the story. Some physicists, like Carlo Rovelli and the proponents of loop quantum gravity, propose a radical scenario. They look at the singularity inside a black hole, another place where our physics breaks down, and ask a powerful question. What if that singularity isn't an endpoint? General relativity predicts it is, but general relativity doesn't include the rules of the quantum world. A true theory of everything, or quantum gravity, would describe what happens at these extreme scales. Under this new physics, the collapse might not be infinite. Instead, the matter crushed inside a black hole could reach a maximum point of compression and then bounce. This is called a quantum bounce. And what would that bounce look like from the outside? It would look like a singularity suddenly reversing its collapse and spewing all of its compressed matter and energy back out. It would look exactly like a white hole. In this black hole cosmology, or Schwarzschild bridge model, a black hole in one universe could act as a seed for a new universe. The matter it swallows gets crushed, undergoes a quantum bounce, and emerges as a white hole, the Big Bang, in a completely separate new spacetime. Our entire universe could be the other side of a black hole that exists in some parent cosmos. This idea is staggering. It suggests that universes might be born from the ashes of dead stars in other universes, a cosmic cycle of death and rebirth on the grandest possible scale. This white hole Big Bang hypothesis is attractive because it offers potential solutions to old problems. For instance, the uniformity of our universe, the fact that it looks roughly the same in all directions, is a puzzle. A white hole origin story could explain this, as the matter would have had time to mix and settle inside the parent black hole before bouncing. It also gives us a before to the Big Bang, something the standard model lacks. However, this is where we must walk the fine line between established science and fascinating speculation. There is currently zero observational evidence to support this. It is a beautiful theory born from the marriage of general relativity and quantum mechanics, but it remains a mathematical dream. The challenges of ever proving it are quite literally cosmic. If our universe was born from a white hole, that event happened 13.8 billion years ago. The white hole itself is long gone, having exhausted its contents to create everything we see. It's like arriving at the scene of an explosion and trying to piece together the exact chemical composition of the bomb from the scattered debris. Furthermore, how could we ever see the parent universe from which our founding black hole came? By definition, it's causally disconnected from us. We are sealed inside our own bubble of space-time. The only potential clues might be hidden in the faint radiation left over from the Big Bang, the cosmic microwave background where some theorists hope to find subtle anomalies or scars that could hint at such a violent bouncing birth. So, while the scientific consensus remains firmly with the standard Big Bang model, the white hole continues to inspire. It represents a frontier of theoretical physics where our most fundamental concepts, beginnings, endings, and the very fabric of reality are up for grabs. It's a powerful reminder that the universe, as described by our equations, might be far stranger and more interconnected than we can possibly imagine. The black hole taught us that there are places where things can end. The white hole, its phantom twin, whispers that those endings might just be new beginnings in disguise. Are white holes real? Or are they just a beautiful mathematical ghost? Perhaps they are a concept waiting for a new generation of physics to fully resurrect them. For now, they remain one of the most profound and unanswered questions we can ask, challenging us to look at the darkness of a black hole and wonder if it's not just an end, but a doorway.